I am Mr. Vishal Murthy Pawar, working as an assistant professor in Department of Chemistry PG. Today we are going to see one topic from the subject CHO 352 stereochemistry and asymmetric synthesis of organic compounds of class MSc second organic chemistry semester third. The name of topic is stereochemistry of epoxide ring formation. In stereochemistry of epoxide ring formation, we are going to consider particularly the epoxidation of halohydrins. As we know that halohydrins are the compounds in which hydroxyl group and the halogen they are on the adjacent carbons, or in halohydrins hydroxyl group and halogen they must be on adjacent carbons. If you treat the halohydrins with a base which gives a epoxide through intramolecular SN2 reaction. In intramolecular SN2 reaction, the incoming nucleophile and the outgoing leaving group they are within the same molecule. If you consider the reaction here, the halohydrins with the hydroxyl group and the halogen on the adjacent carbon when react with the base, there is a formation of epoxide takes place with the evolution of halide ions. Now here we are going to apply this concept of epoxidation of halohydrin to the cyclohexyl system, in which if you consider this reaction in which hydroxyl group is beta oriented and that of the halogen that is bromine is alpha oriented, when react with the base hydroxide ion, that hydroxide ion picks up the hydrogen and with the subsequent formation of the oxide, that oxide when undergo a reaction or particularly intramolecular SN2 reaction. In this case, when that oxide undergo intramolecular SN2 reaction, there is a loss of leaving group that bromine takes place, and there is a formation of beta epoxide take place. As hydroxyl group is beta oriented, here there is a formation of beta epoxide takes place. Now, what is the stereoelectronic requirement of epoxidation of halohydrins in cyclohexane ring? The stereoelectronic requirement is that on cyclohexane ring, the hydroxyl group and the halogen must be trans-diaxial to each other. That is, epoxides are formed most easily from diaxial halohydrides. Remember this stereoelectronic requirement for epoxidation of halohydrins on cyclohexane ring, that is, the hydroxyl group and the halogen they must be trans-diaxial to each other. Now, if you consider one of the example under this case, let's say consider the trans isomer and the cis isomer. To consider the first one, in trans isomer, the acyl alkoxide is favorably located for a rear attack on the carbon bearing the acyl halogen to form epoxide. If you consider the first isomer, trans isomer, in which there are three substances are present. first one is the beta hydroxyl, second one is the alpha chlorine, and at the fourth position there is that tertiary butyl group is present with the beta orientation. If we draw a chain conformation in which there is a axial hydrogen group is there, at the adjacent carbon there is axial chlorine group is there, and at the fourth carbon there is equatorial tertiary butyl bulkar group is there. When that reacts with hydroxide ion, that hydroxide ion firstly react with the axial hydrogen group to form the axial alkoxide, and that axial alkoxide undergo the intramolecular SN2 reaction with the adjacent axial halogen leaving group, so that there is a formation of beta epoxide takes place. The stereochemistry of the epoxide is decided by the stereochemistry of the hydroxyl group. As in the first example, hydroxyl group is beta oriented, that's why there is a formation of beta epoxide takes place. While in second example, as the stereochemistry of hydroxyl group is alpha, there is a formation of alpha epoxide takes place. Whereas in cis isomer, equatorial alkoxide is not well disposed toward rear attack displacing halogen, as we have just seen that this one. Okay, in case of this equatorial one, in this case the hydroxyl group is alpha, that's why it is equatorial. Chlorine is also alpha, that's why it is axial, while the tertiary butyl group which is beta, therefore equatorial. When this treated with the base, as hydroxyl group is at the equatorial position, the equatorial alkoxide is not in well position for the disposal of leaving group axial chlorine. That's why instead of their nucleophilic substitution takes place, the hydrogen at the adjacent position is here migrated, and instead of substitution reaction there is rearrangement reaction takes place, so that there is a formation of 4-tertiary cyclohexanone takes place. Thank you.